Scientists have long pondered the question. What was there before the Big Bang? New findings are now revealing surprising insights. Brian Cox and other experts suggest that the answer may be more complex and unsettling than previously thought. According to Cox, the universe may not have been hot and dense before the Big Bang, as traditionally assumed. Instead, it may have been cold, empty, and expanding rapidly. This initial expansion, known as inflation, set the stage for the universe we observe today. However, inflation did not occur uniformly. It stopped in some regions, creating what we now call the Big Bang, while it continued in other areas. This theory, called the inflationary multiverse, suggests that our universe is just one of many. In this view, the universe resembles a fractal, with countless Big Bangs happening across different parts of space and time, each forming its own unique world. Our universe, then, may be just a tiny portion of a vast, intricate cosmic landscape. So, what exactly is inflation, and why did scientists find it so perplexing? Before the Big Bang, space expanded at a rapid pace, a process called inflation, triggered by a mysterious form of energy. During this phase, space stretched quickly, smoothing out irregularities, which made the universe appear flat and uniform. As inflation ended, the energy driving this expansion was released, heating space and generating the particles that constitute everything around us. Traditionally, scientists believe the Big Bang marked the beginning of all things, but it was, in fact, just one part of the universe's larger story. This raises new questions. What existed before inflation, and why does the universe continue to expand? The concept of absolute emptiness is challenging in the context of the universe's vastness. Even if all energy were removed, the universe would never be completely void. New forms of energy arise as the universe expands, even in the absence of particles, photons, and radiation. Quantum fields, fundamental forces of reality, persist in even the emptiest spaces, ensuring that the universe will never be entirely empty and that radiation will always be generated, even in voids. This suggests that true nothingness is impossible because quantum fields always maintain a baseline presence. Therefore, the idea of nothing before the universe began remains problematic. Some scientists wonder if there was ever true nothingness before the universe. Current understanding suggests that even in the emptiest spaces, some form of energy remains, known as zero-point energy. This is the closest concept to nothingness, but it still represents the lowest level of energy present everywhere. The universe has evolved continuously, with space expanding and galaxies moving farther apart. After the Big Bang, the universe was hot and dense. As time progressed, it became larger, cooler, and less dense. This process causes distant light to appear stretched, resulting in redshift, where light waves elongate as they travel farther from us, dropping energy levels and temperatures. The universe is far colder now than at its inception. Even if all matter and energy were removed, empty space would still be governed by physics, filled with quantum fields, and influenced by dark energy, which drives cosmic expansion. Inflation played a crucial role in shaping our universe's history. Before inflation, a powerful form of energy likely caused space to stretch at unprecedented speeds, smoothing out early irregularities to create a uniform cosmos. This process, however, raises fundamental questions. Where did it begin? If inflation continued indefinitely in some regions, creating countless Big Bangs, how does it shape our understanding of the Big Bang? Answering these questions requires examining three interconnected ideas: the hot Big Bang, the theory of cosmic inflation, and the notion of an ultimate beginning. Astronomers like Edwin Hubble observed galaxies moving away from us in the early 20th century, leading to the realization that the universe is expanding. This observation suggested the universe was much smaller and denser in the past, giving rise to the Big Bang theory, which posits that all matter and radiation originated from an incredibly hot, dense point. However, the Big Bang theory couldn't account for some observed features, like the universe's flatness and uniform temperature. This is where inflation theory comes in, suggesting that inflation created the universe's smooth, flat appearance, while implying the Big Bang wasn't the true beginning but rather a transition from an inflationary phase to the hot, dense state we know today. Despite its insights, the Big Bang theory faces challenges, such as the horizon problem, which refers to how parts of the universe that have never interacted seem to share the same temperature and properties. This implies these areas must have been connected in the past, even though they're now too distant to share information. The flatness problem is another issue. The universe's expansion and gravitational forces are so finely balanced that they create a flat, stable cosmos. Inflation explains both by proposing that rapid spatial expansion smoothed out initial curves. Scientists have long wondered why the universe has its specific properties, and while early theories addressed what occurred during the Big Bang, inflation theory clarifies why the universe is so uniform and why certain particles, like magnetic monopoles, don't exist. The question of what happened before the Big Bang remains open. In 1980, physicist Alan Guth introduced a groundbreaking approach to these cosmological puzzles with the theory of inflation, a period of rapid, continuous growth in the early universe. According to Guth, the universe's energy wasn't yet divided into particles of matter and radiation but was part of space itself, which expanded at extraordinary speeds. Inflation solves three key problems. The horizon problem, by proposing that everything was once closely connected in a small, dense state before rapidly expanding, explaining the universe's uniformity. The flatness problem, by suggesting that inflation erased any original curvature. And the monopole problem, by preventing extreme conditions that could have created unusual particles. Inflation does more than resolve cosmological issues. It also offers clues about the formation of cosmic structures, like galaxies. Tiny quantum fluctuations in space were amplified to cosmic scales during inflation, creating the bumps that later evolved into galaxies, clusters, and stars. Observations of the cosmic microwave background (CMB), the Big Bang's afterglow, and the universe's large-scale structure confirm these early imperfections, which laid the groundwork for everything we observe today. Predictions about these patterns in the CMB, made in the 1980s, have since been validated, strengthening inflation theory as a model for cosmic origins. Yet, inflation raises a profound question. If inflation describes the pre-Big Bang conditions, was the Big Bang truly the beginning? Early Big Bang models suggest the universe began as a singularity, an infinitely dense point, but inflation complicates this picture. Since inflation causes space to expand exponentially, it implies that the universe never actually reached a state of zero size, as the Big Bang model suggests. The idea of a universe starting from a singularity is difficult to reconcile with inflation, as the exponential growth would prevent such a collapse. Evidence only dates back to a brief moment after the start of inflation, marked by quantum fluctuations before inflation triggered the Big Bang. Eternal inflation adds further complexity. In this scenario, inflation never completely ends. It halts in some regions, like our universe, but continues in others, resulting in a multiverse, a collection of countless pocket universes, each with its Big Bang. This process wipes out all records of what might have existed before inflation, making it nearly impossible to understand the universe's origin after that point. While eternal inflation is intriguing, it does not extend backward indefinitely. Studies indicate that expanding spacetime cannot regress infinitely. It likely arose from a prior state, possibly a singular origin, highlighting inflation's limitations and answering the question of where everything originated. Alternative models, like cyclical or bouncing cosmologies, propose that the universe undergoes cycles of expansion and contraction, but they too cannot evade the question of a beginning. What does nothing mean? The notion of nothingness in cosmology isn't as straightforward as it seems. Quantum fields remain active even in the emptiest areas of space. Even without particles or energy, these fields still oscillate and interact, indicating that the closest thing to nothing is still something, a vacuum filled with quantum potential. The vacuum origin hypothesis posits that the universe could have originated from a quantum fluctuation in this vacuum, an idea that has fascinated physicists. This theory suggests the universe began as a fluctuation from nothing, giving rise to everything we observe today. Though speculative, this concept challenges our understanding of existence and nothingness. Quantum fields and virtual particles are also integral to our universe's composition. Quantum field theory posits that energy fields pervade space, combining to form everything from atoms to stars. These fields operate even at their lowest energy level, known as the vacuum state, with virtual particles constantly emerging and vanishing, borrowing energy from the void. These fields and particles are crucial to the universe's structure, yet they complicate our grasp of true nothingness. If space is filled with these dynamic fields, can we ever claim the universe was truly empty? Dark energy, a mysterious force, propels the universe's accelerating expansion. While inflation explains the early rapid expansion, dark energy drives the current growth. Even in the distant future, when stars burn out and matter disperses, dark energy will continue pushing the universe to expand. In essence, the universe has never been empty, and likely never will be. Expansion, radiation, and quantum fields will endure as long as dark energy persists. Scientists have spent decades unlocking secrets about the early universe, and inflation theory has transformed our understanding. But as we've seen, it also prompts new questions. What existed before inflation? What caused it to begin? And why does the universe seem to resist the concept of nothingness? Although we may not yet have all the answers, the search continues, and each discovery brings us closer to understanding the origins of everything in the universe. Stay tuned for more articles on these cosmic mysteries, and share your thoughts in the comments below.